Something entered our solar system this year, quietly at first. A faint speck caught by the automated eyes of an observatory in the Chilean desert, a blip on a sensor that shouldn't have been there. It wasn't a satellite. It wasn't an asteroid we'd tracked before. It moved differently. It moved like a visitor. That discovery, made on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System ATLAS, marked only the third time in human history that astronomers confirmed an object from another star system passing through ours. They named it 3I ATLAS. The 3I stands for Third Interstellar Object. Simple, factual, but the truth behind that sterile name is anything but simple. Because what this object is doing and what it refuses to do has left scientists questioning everything they thought they understood about comets, space, and maybe even the nature of matter itself. To appreciate how strange this is, let's rewind to that first detection. Atlas, stationed in the clear mountain air of Chile, scans the sky each night, looking for anything new, the subtle streaks of motion that could signal asteroids on a collision course with Earth. Its algorithms noticed a faint, fast-moving light that didn't fit the usual patterns. Over the next few nights, astronomers tracked it and ran the numbers. Its orbit didn't loop around the Sun like a planet or comet from our own system. Instead, it followed an open, hyperbolic trajectory, meaning it wasn't bound to our star at all. It came from interstellar space, was passing through once, and would never return. That single calculation changed everything. Because when you plot an orbit like that, it tells you one thing: this object doesn't belong here. Interstellar objects are almost mythic in astronomy. For centuries, they were theoretical wanderers between stars, ejected from their birth systems by gravity or collision, drifting alone for millions, maybe billions of years. We never expected to actually see one up close. Then, in 2017, we got a surprise. Oumuamua, the first interstellar visitor ever recorded. A cigar-shaped mystery that tumbled through the inner solar system and left just as quickly, confusing scientists with its lack of visible outgassing. 2 years later came 2I, Borisov, much more like a traditional comet with gas and dust and a visible tail. Now, 3I Atlas has arrived, bigger, brighter, and far stranger than either of them. From the beginning, it didn't fit the mold. Its incoming speed was enormous, far beyond what a comet from our solar system could achieve. And its direction of arrival pointed back toward a region of the galaxy we haven't fully mapped for interstellar debris. It wasn't following the galactic plane like most long-period comets. It was cutting through space at a skewed angle, as if it had been wandering aimlessly for ages, buffeted by the gravity of countless stars before finally stumbling into ours. NASA's analysis confirmed that this wasn't some stray rock kicked out of the Oort cloud. It was moving too fast and from too far away. It was truly interstellar. But that's just the surface of the mystery. Because as astronomers gathered more data, they noticed something deeply unusual. Its brightness wasn't behaving normally. Most comets brighten predictably as they approach the sun, as sunlight vaporizes ice and dust. But 3I Atlas, its light curve was chaotic, flaring, fading, then flaring again like a signal trying to stabilize. It didn't take long for scientists to realize they were watching something that might rewrite the rulebook. Interstellar doesn't just mean from another star. It means an object that has survived the longest journey imaginable. Think of it. A piece of material formed around an alien sun, possibly long before Earth even existed, flung into space by some ancient gravitational accident. For millions of years, it drifted through absolute darkness, through radiation, magnetic storms, and the cold vacuum between stars. Every atom of its surface has been bombarded by cosmic rays older than our species. Every molecule has been twisted and broken by time itself. And now, after all that, it has entered our solar system, and we get to watch what happens when something truly alien meets the heat of our Sunday. At first, scientists expected a show. As 3I Atlas approached perihelion, its closest point to the Sun, the heat should have caused its frozen gases to erupt, creating a tail of dust and vapour. That's standard comet physics. But what happened next didn't match any model. The object flared. Its brightness spiked suddenly, not gradually, not predictably, but explosively. Then it stabilized and refused to break apart. Even after taking a direct blast of solar radiation, 3I Atlas stayed intact. It didn't flinch. That's the moment this story changed from interesting to historic. Because whatever this thing is made of, it's not behaving like a comet from our solar system. The standard rules, the sublimation curves, the energy thresholds, the dust behavior, none of them apply cleanly. And that has scientists asking a dangerous question. What is this thing really made of? NASA's early spectroscopy hinted at something odd, a chemical composition that looked both familiar and wrong at the same time. Carbon compounds, yes, but in ratios we don't usually see. Some elements seem suppressed, others overrepresented. The spectral signature didn't align with any known catalogue of comets. It looked like the fingerprints of a material forged in conditions utterly different from our Sun's neighbourhood. Imagine a comet formed around a red dwarf star, or in the outer reaches of a binary system where the radiation environment is different, the chemistry alien. Over billions of years, cosmic rays could have transformed its surface into something almost metallic, a crust hardened by radiation, protecting an untouched core within. When it entered our system and met the Sun's heat, maybe that crust cracked, releasing gases in unpredictable bursts. Maybe that's what we're seeing, a reaction from a material we've never tested, behaving in ways we can't yet simulate. But there's another possibility, one far stranger, and one that no scientist is comfortable proposing outright, that 3I Atlas is not purely natural in structure, not artificial in the sci-fi sense, but perhaps the remnant of processes we don't yet understand. Interstellar chemistry is not uniform. There are regions of molecular clouds where reactions proceed differently, where radiation, magnetism, and particle density create compounds we've never observed in the lab. What if this object is the fossil of one such process, a chunk of matter shaped by a different cosmic recipe? These are the questions now driving the teams at NASA, ESA, and the Royal Belgian Institute for Space Astronomy. Because every telescope, every sensor, every spectral scan tells the same story. This object is different. And that difference matters. Because if we can figure out why 3I Atlas behaves this way, why it brightens explosively, why it resists disintegration, why its chemistry seems out of place, we might glimpse something far more profound than a comet. We might be looking at the physical memory of another star system, a time capsule from a place we can't yet reach. Over the coming weeks, as it swings around the Sun and begins its long exit back into interstellar space, 3I Atlas will give us our only chance to study it up close. Once it's gone forever, another spark vanishing into the dark between worlds. But for now, it's here, a visitor from beyond, glowing blue-white against the void, refusing to behave, refusing to explain itself. And as it endures the fury of our Sun, a direct solar storm hit that would shred any ordinary comet, one question echoes louder than all the others. What exactly is 3I Atlas? And why does it seem to survive what nothing else should? When scientists first plotted the orbit of 3I Atlas, they realized immediately that they weren't looking at a normal solar system trajectory. It wasn't looping, it wasn't curving gracefully around the sun like an asteroid or a long-period comet. It was slicing through the plane of the solar system at an angle that made no sense. The object came in on a steep, hyperbolic path, meaning its eccentricity was greater than 1, the mathematical signature of something not gravitationally bound to our Sunday. In simple terms, once 3I Atlas came in, it was never coming back. Its orbit is open, not closed. That one fact already made it special. But it was the details of that orbit, the speed, the direction, the timing, that turned it into one of the most baffling celestial events in recent history. Let's start with speed. At discovery, 3I Atlas was hurtling through space at around 95,000 miles per hour relative to the Sunday. That's more than double the average speed of a typical long-period comet. By the time it approached perihelion, its closest point to the Sun, it accelerated to over 230,000 miles per hour. That's not unprecedented, but what's remarkable is the approach angle. It wasn't coming from the usual direction of our solar system's motion through the galaxy, known as the solar apex. It was coming from a skewed vector high above the ecliptic, the flat plane where most planets orbit. That's odd because the first interstellar visitor, 1I, Oumuamua, had come from roughly the solar apex direction, as if it had been moving along the galactic flow of nearby stars. The second 2I, Borisov, came from a different but still fairly aligned region. Both could plausibly have been ejected from nearby stellar systems within the Milky Way's general disk. But 3I Atlas, its path suggests it came from outside that flow, possibly from above or below the galactic plane, meaning it might have wandered for eons in the galaxy's halo region, a place populated by ancient metal-poor stars and fragments from long-dissolved systems. If that's true, then 3I Atlas isn't just from another star system, it might be from another era of the galaxy itself. Now, when astronomers at the Debrief and other scientific outlets started analysing the orbital parameters, they found something else. The inbound velocity of 3I Atlas was unusually stable. Most comets or small bodies show subtle perturbations as they interact with the gravitational fields of planets along their approach, small tugs that slightly alter their paths. But 3I Atlas seemed unbothered. Its inbound trajectory barely changed, even after passing near Jupiter's region of influence. That level of inertial steadiness implies a large mass, or at least an extremely dense nucleus compared to typical comets. Then came the early size estimates, courtesy of the VERA-C, Rubin Observatory's new imaging array. Using reflected light curves and thermal modelling, astronomers estimated that 3I Atlas might be up to 11 kilometers wide, about the size of Mount Everest. That's nearly 10 times larger than Oumuamua and significantly larger than 2I Borisov. And remember, larger means more inertia, more internal structure, more gravitational integrity. Put simply, this is not a fragile snowball of ice and dust. It's something built to last. And yet, for all that size, its surface reflectivity, its albedo, is shockingly low. It's dark, almost coal-like, reflecting less than 4% of the sunlight that hits it. That combination, big, dark, and fast, is extremely rare. It makes 3I Atlas almost invisible until it's already close. That's why we didn't spot it until it was already on its inbound leg toward the inner solar system. Now, let's compare it directly to its predecessors. Oumuamua was small, probably less than 400 meters in length, and it had no visible coma or tail, a mystery that led to endless speculation about whether it was a rock, a shard of something larger, or even an artificial object. It also had an odd acceleration that couldn't be fully explained by outgassing. 2I, Borisov, by contrast, behaved like a textbook comet. It released water vapor and dust, forming a clear tail, and its chemical makeup looked familiar: carbon monoxide, hydrogen cyanide, and water, all standard Comet ingredients. Then comes 3I Atlas, and it refuses to pick a side. It has the mass and stability of a rock, the spectral hints of ice, but the behaviour of something else entirely. Its outgassing patterns are uneven, its chemical signals dominated by carbon dioxide far more than any comet we've catalogued. In fact, NASA's early analyses suggest that CO2 may be the dominant volatile, which implies that much of its surface water ice is either gone or sealed under a hardened crust. This CO2 richness is particularly interesting because carbon dioxide sublimates at lower temperatures than water ice. That means 3I Atlas could have started releasing gas far earlier in its journey toward the Sun, possibly while it was still billions of kilometers away. And yet, when it got close enough for solar heating to peak, instead of gradually increasing its activity, it exploded in brightness. That contradiction, early, steady CO2 activity followed by a late, violent outburst, tells scientists something profound. The surface isn't homogeneous. Different layers are responding to the sun's heat in completely different ways. That points to a complex internal structure, maybe even multiple composition zones formed in distinct regions of its parent star's protoplanetary disk. And that leads us to the next question: what does its launch tell us? Interstellar objects don't just drift into space by accident. To escape a star's gravity, something must give them a colossal kick, usually a close gravitational encounter with a giant planet or a catastrophic impact. For 3I Atlas to be travelling this fast and from this angle, the most likely scenario is that it was ejected from a young, unstable system where planetary migration or collisions violently expelled material into interstellar space. That could have happened billions of years ago. So when we study its trajectory and composition, we're not just studying a comet, we're reverse engineering a foreign solar system. Every element in its movement, its speed, its tilt, its composition is a clue about the physics of that long-lost home. But here's where things get complicated. Theoretically, when an interstellar comet enters our system, we can use its trajectory to trace it back to a region of the sky, a rough point of origin. With 3I Atlas, astronomers tried and hit a dead end. Its incoming vector passes through a crowded section of the galactic plane with no obvious source stars close enough to match its timeline. The conclusion? It's been travelling for so long that its path has been bent and deflected by the gravitational fields of multiple stars. Its birthplace may no longer exist, and that realization has a certain poetry to it. This isn't just a visitor. It's a survivor of galactic drift, a messenger from a system that might have died before humanity ever looked up. Yet, for all that romanticism, the scientific mystery remains. Why does it behave this way? Why does it defy the models? Why does it survive conditions that should obliterate it? Early polarimetric studies showed an unexpectedly low degree of light polarization, suggesting that the particles in its coma, the dust and gas clouds surrounding it, are unusually small and uniform. That uniformity could hint at intense cosmic ray processing, which would pulverize surface material into fine, compact grains over billions of years. So maybe this object's surface is a crust of dust welded together by radiation, shielding the deeper layers. But that only raises more questions. How thick is that crust? What's trapped underneath? And why is its CO2 escaping through isolated jets instead of diffusing evenly? Every orbit plot, every brightness curve, every spectral line seems to contradict something else. It's as if the universe is playing a game of cosmic misdirection, showing us fragments of truth, never the full picture. We thought a visitor from another star system would be straightforward, a relic of alien geology, sure, but still bound by the same physical laws we know. Instead, 3i Atlas is teaching us that the laws we thought were universal might have local exceptions shaped by the chemistry, magnetism, and radiation environment of a different sun entirely. Its path tells us where it came from. Its speed tells us how long it's been alone. And its refusal to behave tells us that somewhere out there, in the quiet dark between stars, nature is still capable of surprises. 3i Atlas doesn't just move fast, it moves against expectation. And the deeper we study that motion, the more we realize this object isn't simply passing through our solar system, it's passing through our understanding of the universe itself. When astronomers first aimed their spectrographs at 3i Atlas, they expected to see something familiar, a spectrum dominated by water vapor, the telltale fingerprint of solar heating breaking ice into steam. But what came back from the instruments wasn't familiar at all. It was dominated by carbon dioxide. That discovery alone would have been surprising enough. CO2 carbon dioxide is common in comets, yes, but not in such enormous quantities. In fact, the ratio between CO2 and H2O in Atlas's coma, the faint gas envelope surrounding it, was completely inverted from what's typical. For most solar system comets, water is the major volatile. CO2 is a minor contributor. But for 3i Atlas, it seemed the opposite was true. CO2 emissions were outshining water by a factor of several to one. This immediately set off debates across the planetary science community. The data were first confirmed by ground-based observatories in Chile and later refined through high-resolution spectra from the James Webb Space Telescope. Webb's infrared sensors revealed an abundance of CO2 absorption lines and a relative lack of the familiar H2O bands expected at those wavelengths. So what could cause a comet to behave like that? One idea points to the temperature and composition of the star system it came from. In our own solar system, comets form in the cold outer regions, the Kuiper belt and Oort cloud, where water ice is abundant. But if 3i Atlas formed closer to a dimmer or redder star, one with a cooler protoplanetary disk, CO2 could have been the dominant ice available. In such an environment, carbon dioxide becomes the primary building block of frozen bodies. That alone would mark it as a child of a very different kind of sun. But that's not where the weirdness ends. Polarization studies, measurements of how sunlight scatters off the dust, showed something completely unexpected. The light coming off Atlas's coma was highly polarized at certain angles, far more than seen in any comet before it. That kind of polarization implies an unusual surface texture, something rough, complex, perhaps coated with a layer of irradiated material. Researchers at the Royal Belgian Institute for Space Astronomy published an analysis suggesting that cosmic rays travelling through interstellar space for millions or billions of years might have reshaped the comet's outer layers into a dense, carbon-rich shell. Over time, these high-energy particles could have stripped away hydrogen, leaving behind a kind of blackened, chemically altered crust. The result, an irradiated skin tens of meters thick, under which pristine ices might still be hiding. That idea, an irradiated crust, helps explain another mystery, why the water signal was so faint. If water ice beneath the surface was sealed under a carbonized layer, it might take significant heating for it to vent out. And when the comet finally did erupt near perihelion, that could have been the moment when that crust cracked open, exposing fresh ice and releasing the huge burst of brightness that astronomers later called the solar flash. But the chemistry hints at something deeper. When the JWST and supporting ground-based telescopes examined the ratios of carbon monoxide CO to carbon dioxide C, they noticed something striking. The CO2 levels were high, but CO, which should accompany it if both ices form together, was relatively low. That mismatch doesn't fit well with models of cometary evolution. Instead, it suggests a complex thermal history. Maybe 3I Atlas was once heated by its home star, lost some of its CO, then was flung outward frozen mid-transformation before escaping entirely into interstellar space. If that's true, we're looking at a snapshot of planetary formation gone wrong, a world that almost became something, perhaps a protoplanet or a fragment of a disrupted icy moon before being hurled into the void. And that brings us to the next mystery, the isotopes. Early isotopic analysis of the gases indicated ratios of carbon 1,3 and nitrogen 1,5 that don't match anything measured in solar system comets. It's as if Atlas was forged from ingredients we simply don't have here. That's not poetic exaggeration, it's literal chemistry. Different stars fuse elements in slightly different proportions, leaving subtle fingerprints in the material that forms around them. The chemistry of 3I Atlas may therefore tell us which kind of star, maybe even which kind of stellar nursery it came from. So, where did it form? In a colder, darker system, orbiting a red dwarf? In the volatile-rich outer disk of a binary star? We don't know yet. But what we do know is that its chemical fingerprint does not resemble the solar system's icy bodies. Its surface is darker, its gases are stranger, and its structure may be more complex than anything we've catalogued before. By the end of July, the consensus forming among researchers was uneasy. 3I Atlas isn't just another interstellar comet like Borisov. It's chemically alien, a product of an environment that may have operated under entirely different rules of chemistry and temperature. And that leads to a haunting question. If its chemistry is so different, what does that say about its origin story? Is this the fragment of a long-dead planetary system, a shard of something ancient preserved in deep space? Or could it be a kind of messenger carrying signatures of organic chemistry we've never encountered before? Because buried beneath that irradiated crust, beyond the CO2 haze and the strange polarization patterns, could be something extraordinary. Frozen relics from a star that died long before ours was born. And if that's the case, then every molecule venting off 3I Atlas right now might be whispering a story from another world, one that, for the first time in history, we can finally hear. But the chemistry only deepens the puzzle. When the comet flared near the Sun, something happened that no model predicted. It wasn't just a surge of gas. It was structural. Something inside the nucleus changed violently, abruptly, and perhaps irreversibly. Before it ever crossed paths with our Sun, before it lit up telescopes and headlines, 3I Atlas had already been travelling for eons. Not centuries, not millennia, but potentially billions of years. Imagine that. An object no wider than a small mountain, drifting silently between the stars, carrying the frozen memory of a world that no longer exists. It would have seen nothing, heard nothing, felt nothing, except the faint, invisible bombardment of the galaxy itself. That bombardment comes in the form of cosmic rays, high-energy particles, accelerated by supernovae, magnetars, and ancient stellar winds. These particles, moving at nearly the speed of light, can tear through rock and ice like microscopic bullets. Over time, they change everything they touch. For 3I Atlas, this wasn't a short exposure. It was a relentless cosmic sandblasting that lasted longer than all of recorded human history combined, multiplied by millions. Astronomers believe that this interstellar radiation exposure fundamentally transformed the comet's outer shell. Studies from the Royal Belgian Institute for Space Aeronomy, along with modelling from NASA's Cosmic Dust Laboratory, suggest that cosmic rays likely penetrated 15 to 20 meters into the comet's surface, maybe even deeper. At that depth, they didn't just damage the ice, they rewrote it. When high-energy cosmic rays strike frozen molecules, they split them apart, forcing them to recombine in new, unnatural ways. Hydrogen gets stripped away, oxygen binds with carbon, and over unimaginable stretches of time, what was once white, reflective ice becomes black, carbonized crust. The result is what scientists call a deep irradiated layer, a hardened, chemically altered shell that no longer resembles the pristine material from which the object was born. So when we observe 3I Atlas today, we may not be seeing its origin, we're seeing the product of its journey. Think of it like an ancient spacecraft, drifting for billions of years through interstellar space. Every cosmic storm it passed through, every magnetic wave, every charged particle, all left microscopic scars on its hull. By the time it finally arrived here, that hull was no longer the shining metal it once was. It had been reshaped, darkened, hardened, a relic of endurance rather than design. That's 3I Atlas. Not a messenger from another solar system, but a survivor of the void between them. This weathering effect also changes how we interpret the light it reflects. Because its outer layers are no longer the same material that formed around its original star, spectroscopic analysis only tells us half the story. The chemistry we see on the surface, rich in CO2, depleted in water, low in volatiles, may represent the history of cosmic ray exposure, not the conditions of its birth. That's a profound realization. It means when astronomers first looked at its spectrum, they might have been studying the scars of the voyage, not the fingerprints of its creation. The question now is, how deep does that damage go? Computer simulations of cosmic ray penetration suggest that while the outer 50 or so feet of 3I Atlas may be radically transformed, the core could still be untouched, sealed away since the dawn of its existence. Inside that core, locked beneath the irradiated shell, could lie the original material from its home system, still preserved as it was billions of years ago. And that's where the real mystery lies. If the outer layers are a story of survival, the interior could be a story of origin. That hidden nucleus might hold ancient organics, amino acids, hydrocarbons, or other complex molecules that predate our Sunday. It might even show that chemistry in distant systems isn't all that different from our own, or perhaps that it's completely alien. But there's something eerie about this concept, because if we can't see past the crust, we're like archaeologists staring at a sealed sarcophagus from a lost civilization, unable to open it. Every layer of cosmic damage tells us something about the journey, but it also hides the truth of what lies beneath. Some astronomers have described 3I Atlas as a fossil of interstellar travel. That's not poetic, it's literal. Its surface is a geological record of its time in deep space. Each radiation strike, each chemical alteration is like a timestamp marking where it's been. Think about that for a second. A small icy object, no larger than a mountain, drifting from star to star for billions of years, its crust silently encoding the map of its odyssey in chemistry and carbon. When we finally caught it entering our solar system, we didn't just capture a visitor, we intercepted a record of the galaxy itself. And yet, the paradox remains. The more we study it, the less we seem to know about what it truly is. Because everything we can measure, every light signature, every gas emission, has already been rewritten by time and radiation. That leads to the most tantalizing question of all. What's inside? Is there still pristine ice, untouched since the day it formed around another sun? Are there trapped gases that might tell us what kind of star it once orbited? Could there even be the faintest traces of prebiotic chemistry, the same kind of ingredients that may have seeded life here on Earth? We can't yet know. But one thing is certain. When we look at 3i Atlas, we're not just seeing a traveller, we're seeing time itself made visible. Its crust tells the story of its journey. Its gases tell the story of transformation. And its hidden core, whatever's left untouched, may tell the story of creation. In the next chapter, we finally reach the moment that changed everything. When 3i Atlas met our Sun, it wasn't a gentle encounter. It was a collision of extremes: radiation, magnetism, and heat. And the result would defy every expectation. Every astronomer on Earth knew what was supposed to happen. When a comet nears the Sun, the script is simple, and it's been replayed thousands of times throughout history. The ice heats up, frozen gases sublimate, turning straight from solid to vapor. Pressure builds within cracks and pockets, forcing jets of gas and dust into space. A coma forms a glowing shroud of vaporized material, and the classic tail stretches away, driven by the solar wind. That's the physics every student of astronomy learns. Predictable, elegant, and for a while 3i Atlas seemed to follow that script until it didn't. As the interstellar visitor closed in on its closest approach to the Sun, its activity didn't just rise steadily, it detonated. Its brightness, which had been climbing at a modest rate, suddenly surged by more than a factor of 2 within days. The increase was too fast, too intense, and far too early. The object wasn't supposed to react like that yet. Ground-based observatories in Chile and Hawaii, along with space-based coronagraphs like SOHO, Stereo A, and GOES 19, all caught the same event: a sudden, uncontrolled brightening. The comet didn't gently flare, it erupted. Within a narrow window around perihelion, the point of closest approach Atlas began releasing gas at a rate that stunned researchers. Models estimate the outflow of water and volatiles increased by tens of times compared to just weeks earlier. To visualize that, think of a mountain-sized iceberg suddenly turning into a high-pressure fire hose, spewing billions of tons of vapor every second into the vacuum of space. One researcher described it as if the comet had opened a vent straight into its heart. But the bigger shock came not from how much gas it released, but what was missing. When astronomers processed the coronagraph images, they expected to see the unmistakable fan of a dust-tail sunlight scattering off grains of silicate and ice, streaming away from the nucleus. Instead, the images showed something different: an elongated, ghostly glow, but no visible dust tail. No solid debris, no fine dust scattering sunlight, just a stretched out, blue-white emission, pure gas, without the dusty haze. That absence made no sense. Dust is what makes comets beautiful, it's what turns them into those glowing streaks across our skies. But Atlas seemed to have skipped that step entirely. So what was happening? To understand why this is so strange, we have to remember what makes comets tick. Cometary outgassing isn't just about heat, it's about structure. Ice near the surface melts first, releasing trapped dust and gases. But deeper layers stay sealed until the heat wave penetrates. That process creates gradual, predictable changes in brightness. 3i Atlas, however, behaved as if the entire outer crust failed all at once, as if a pressure buildup ruptured a seal, venting material in a single catastrophic event. It was as though the comet had been holding its breath for eons and finally exhaled. One proposed explanation is that the CO2-driven sublimation, the same mechanism we discussed earlier, played a major role. For months, the surface may have been venting carbon dioxide at a steady rate, forming a thin, refrigerated layer that prevented deeper water ice from heating up. But as the comet neared the Sun, That CO2 reservoir might have been depleted. Without it, the protective layer vanished and the underlying ices were suddenly exposed to unfiltered solar radiation. The result? A violent surge of water vapor and energy release. But even that doesn't fully explain the missing dust. If the object really lost that much gas, it should have dragged enormous amounts of dust with it. The absence of that tail suggests something even more unusual. The dust wasn't there to begin with. Maybe the interstellar radiation that sculpted its crust also welded the outer material together, compacting it into something like rock or tar. In that case, there wouldn't be any loose grains to eject. Instead, the gas would escape through microfractures in a sealed surface, creating jets of vapor with almost no solid debris. That hypothesis aligns with observations from Webb's NIRCam instrument, which found that Atlas's coma had an unusual polarization consistent with fine gas molecules, not solid dust particles. But there's another angle, one that's even stranger. Some scientists have proposed that 3I Atlas's nucleus may be porous but cohesive, a kind of sponge-like matrix of irradiated carbon compounds and frozen gases. If the internal pressure reached a breaking point, the entire structure could have momentarily flexed or fractured, producing a massive venting event that temporarily reshaped its outer layers. In other words, the explosion of brightness might not have been a simple outburst. It could have been a partial collapse of the comet's shell, followed by rapid gas expansion through newly opened fissures. If that's true, it's not just an ordinary comet misbehaving. It's something physically unique, an object whose internal structure has evolved over billions of years in interstellar space, now responding violently to the first sunlight it's seen in ages. Astronomers often talk about comets as time capsules, frozen records of early star systems. But what happens when that capsule is cracked open after a cosmic lifetime in the dark? What does the first light of a foreign sun do to something that's been frozen longer than Earth itself has existed? 3I Atlas gave us a glimpse of that. And it wasn't a gentle reawakening. The numbers alone were staggering. In the span of a few weeks, estimates of its water output jumped from roughly 10 to the power of 27 molecules per second to nearly 10 times that rate, enough water to fill an Olympic swimming pool every few minutes, blasting straight into space. And yet, despite that furious loss, the nucleus didn't disintegrate. It held together. That's what left astronomers speechless. Because when comets in our solar system flare that violently, they often fragment or completely fall apart. Atlas didn't. It absorbed a full solar onslaught, heat, radiation, and gravity, and kept going. That's where the story takes an even stranger turn. The sun was acting as the trigger, but Atlas wasn't responding like any known material. The energy exchange was off. The light curve was nonlinear, and the emission spectra showed weird oscillations in brightness that didn't match any rotational model. Something about the nucleus, its density, its bonding, or its internal heat transfer allowed it to endure what should have destroyed it. In a sense, this was a test, a cosmic stress test of matter forged under alien conditions, and it passed. The comet had faced direct solar fire and refused to shatter. The object from another star had stared into the sun and didn't flinch. That resilience raised a chilling question among researchers. What exactly is this thing made of? Because if this wasn't ordinary ice and dust, if the crust could withstand that kind of energy flux, then we might be looking at a type of interstellar material we've never seen before, something born in the chaos of another system's destruction, hardened by the emptiness between stars. And if so, then what happened next after the flare might tell us whether that resilience was just strength or something deeper. When news broke that 3I Atlas was brightening faster than expected, the world's observatories went into overdrive. Within hours, observation time was being reallocated, proposals were being rewritten mid-flight, and astronomers from more than 30 institutions began coordinating what would become one of the most intense global observation campaigns in modern astronomy. Because when something from another star system passes through our cosmic backyard, you don't wait, you watch. It started with the ground-based networks, Chile's Very Large Telescope, the Subaru Observatory in Hawaii, the Lowell Discovery Telescope in Arizona, and the Lulin Observatory in Taiwan all began tracking the object. Each used different instruments, some measuring brightness, others capturing spectra, others recording polarization angles. But this was no ordinary comet, and the instruments themselves weren't enough. 3I Atlas was heading toward perihelion, coming dangerously close to the Sun from Earth's perspective, which made it nearly impossible to observe in visible light from the ground. The only way to truly see it was to look from space, above the glare of our atmosphere, using telescopes designed to stare into the blinding region near the solar disk. That's where Hubble and the James Webb Space Telescope came in. The Hubble Space Telescope, though aging, is still one of the most powerful visible light instruments ever built. Its operators scheduled a rapid response program to catch 3I Atlas before it dipped too close to the Sun's glare. Over the course of several days, Hubble captured faint, high-resolution images showing a narrow, elongated glow, the same dustless structure noted earlier. When the images were enhanced, something became apparent. The brightness distribution wasn't smooth. It had striations, faint ripples of light intensity, suggesting localized jets or filaments of gas venting from the nucleus. This supported the theory that the surface wasn't uniformly active, but fractured and releasing bursts of material through narrow channels. But what those channels were made of, or why they didn't release any dust, remained unclear. While Hubble handled the visual spectrum, Webb took on the infrared. Using its near-infrared spectrograph and mid-infrared instrument, the telescope gathered detailed chemical fingerprints of the gas cloud surrounding the comet. The results were shocking again. Webb's spectra showed strong signatures of carbon dioxide, CO2, ammonia, NH3, and traces of methanol, but a strikingly weak signal for water vapor, H2O. That imbalance, CO2 dominating over H2O, reinforced the idea that the comet's composition was fundamentally alien. In our solar system, water is the first thing to sublimate as comets near the Sunday. Here, it seemed like the hierarchy was inverted. Even more intriguing, Webb detected cyanide-bearing molecules, specifically CN and HCN, but their ratio was off compared to typical comets. The nitrogen chemistry looked skewed, possibly another hint that 3I Atlas formed in an environment with very different temperatures and radiation exposure. Another odd result came from Webb's polarimetric measurements, essentially how light scatters and becomes polarized as it bounces off tiny particles. Normally, comets show a predictable polarization curve that reveals the size and composition of their dust grains, but 3I Atlas's polarization didn't fit any known model. The pattern implied that the light was scattering off molecules and micro-ice clusters, not solid dust. It was as if the comet had lost its grains, not just metaphorically, but literally. Getting this data wasn't easy. Observing near the Sun is one of the hardest feats in astronomy. Instruments must deal with extreme glare, thermal risk, and even potential damage to sensors. Spacecraft like SOHO and Stereo A, built specifically for solar observations, use coronagraphs, special masks that block the Sun's disk to reveal faint structures nearby. But these instruments weren't designed for delicate spectral analysis. They give us brightness and shape, not chemistry. That's why Webb's contribution was so rare. It wasn't built to look near the Sun either. Engineers had to calculate the safe pointing windows carefully so the spacecraft's mirrors wouldn't be flooded with sunlight. It was a high-stakes observation, one mistake, and a $10 billion telescope could be blinded. The result, however, was worth it. Meanwhile, on Earth, hundreds of amateur astronomers joined the effort, uploading daily images and photometric readings to global networks like the Minor Planet Center and the Comet Observation Database. Small observatories across Asia and Europe coordinated follow-ups, trying to capture light curves before sunrise or after sunset, sometimes imaging through bright twilight just to grab a few minutes of visibility. Teams at Michigan State University, ESA's Near-Earth Object Coordination Center, and NASA's Planetary Defense Office were sharing data almost in real time, piecing together a 24-hour watch cycle. It was one of those rare moments in science where every continent was looking at the same mystery, from professional astrophysicists to backyard observers, because this wasn't just another comet. This was only the third interstellar object ever discovered. Oumuamua, the first, had passed too quickly to capture in detail. Borisov, the second, was closer to a traditional comet, but still chemically odd. But Atlas, this one was bright enough, close enough, and visible long enough that humanity finally had a chance to study an interstellar visitor in unprecedented detail. It was, as one astronomer put it, a once-in-a-century encounter. And yet, even with all the world's eyes on it, the data didn't bring clarity. It brought contradiction. The infrared spectra said one thing, the visible light brightness curves said another, polarization patterns didn't match the expected outgassing behavior. The heat models predicted a certain rate of expansion, but the brightness evolution completely defied it. When scientists tried to reconstruct the comet's energy budget, comparing how much sunlight it absorbed to how much it emitted, the numbers didn't add up. The comet was radiating more energy than it should have been able to absorb. That anomaly sparked a flurry of new theories. Could the irradiated crust have trapped heat and re-radiated it unevenly? Was the nucleus spinning irregularly, exposing new vents in pulsars? Or, as a few whispered in late-night conference threads, was there something else, some process we hadn't yet recognized, releasing energy from within? Whatever the explanation, the observations didn't simplify the mystery. They made it bigger. For every new image, every spectral peak, every data point, a new question emerged. And as 3I Atlas began to drift away from the sun, fading slowly back into the darkness, astronomers realized something profound. They had captured the most detailed observations of an interstellar object in history and still had no idea what it truly was. For decades, scientists dreamed of studying a visitor from another star system, a cosmic message in a bottle drifting through interstellar space. The assumption was simple. If we could analyze such an object, we'd glimpse the raw material of another planetary nursery, frozen and preserved across eons. That dream arrived with 3I Atlas and then shattered. Because instead of giving us clarity, this third interstellar visitor forced us to question one of the most comforting ideas in planetary science, that the universe's debris carries clean, untouched information about where it came from. Before Atlas, astronomers treated interstellar comets as time capsules, objects formed around alien suns, flung out by gravitational encounters, and then drifting across the galaxy, unchanged until they stumbled into ours, like fossils in the dark. But 3I Atlas told a different story. Its chemistry, dominated by CO2, with vanishingly little water, suggested not preservation, but transformation. Its brightness outbursts hinted at internal stresses and volatile layering that didn't match any known formation pattern. Even its polarization data implied a skin hardened by relentless cosmic radiation, a crust more armor than surface. That led researchers to a sobering conclusion. Maybe interstellar objects aren't records of their birthplaces. Maybe they're records of their journeys. Billions of years adrift between stars mean billions of years of radiation exposure, atomic collisions, and temperature extremes. Over time, those conditions could alter the molecular structure of the surface, burn away lighter elements, and rearrange the very chemistry that once defined the object's origin. So when we look at 3i Atlas, we might not be seeing a messenger from another system. We might be seeing what's left after the message has been erased. Cosmic rays, high-energy particles that constantly sweep through the galaxy, are thought to sculpt an irradiated skin on objects like 3i Atlas. This crust can reach meters in depth, altering molecules, welding dust, grains, and turning organic compounds into carbon-rich residue. Laboratory experiments simulating these effects have shown how interstellar radiation can convert simple ices into complex polymers, tar-like substances that no longer behave like ice at all. Over eons, a once ordinary comet nucleus could become a hardened relic, its volatile materials trapped beneath an ancient shell. That means the moment an object like Atlas crosses into a new star system, it's not a pristine comet anymore, it's a veteran traveller. So the explosion Atlas experienced near the Sun may have been the breaking of that cosmic armour, a sudden venting of pressure built over epochs. Its odd chemical profile, the dominance of CO2, might represent the gases still able to escape through that crust, not the full inventory of what lies within. If that's true, then every interstellar object we ever detect is already halfway transformed, rewritten by time and radiation long before we meet it. That realization has profound implications. For decades, astrophysicists have built models of planetary formation using the idea that comets preserve the chemistry of their birthplace, the ratios of water, carbon monoxide, nitrogen compounds, and silicates all pointing back to temperature and distance from a star. If interstellar objects no longer follow those rules, then they're not reliable samples of their original systems. Instead, they're evidence of what happens between the stars, the chemistry of endurance, not creation. This challenge is more than just cometary science. It ripples outward into astrobiology, planetary chemistry, and even the search for life itself. Because if cosmic radiation can rewrite molecules so completely, then interstellar organic material, once a promising delivery system for life's building blocks, might arrive here already altered or inert. The same radiation that builds complex organics can also sterilize them. So if panspermia, the seeding of life between star systems, ever happened, it must have overcome a nearly impossible gauntlet of destruction. 3i Atlas reminds us, the galaxy is not gentle. It's a crucible. The deeper scientists looked into Atlas, the clearer the pattern became. This wasn't a one-off anomaly. It might be the rule. Think of 1i, Oumuamua, its mysterious acceleration, its lack of visible outgassing. Think of 2i, Borisov, chemically normal, but unusually active for its size. Now add Atlas, violent outburst, strange composition, and altered surface. 3 interstellar visitors, 3 surprises. That's not coincidence. It's evidence. It suggests that the galaxy's wanderers aren't consistent or predictable. They're a wild archive of everything the cosmos can do to matter over immense time. Every interstellar object is a unique artifact, shaped by both birth and voyage, the physics of formation fused with the chaos of exposure. We used to think interstellar comets were messengers. Now we know they're survivors. So what do we really want to learn from the next one? Should we focus on where it came from or what it became? Should we look for signatures of alien systems or for universal processes that reshape everything that leaves home? Scientists are already rethinking detection priorities for the upcoming Vera Rubin Observatory, which will scan the sky nightly Instead of just cataloguing positions and orbits, some researchers now want to include early infrared characterization, a way to catch an interstellar visitor before it's too altered by the sun's heat. Because with Atlas, by the time we saw it clearly, much of its original story was already gone. This realization forces us to redefine what a sample means. In deep time, purity is a myth. Every cosmic fragment carries the scars of what it's endured. And those scars, in their own way, are information, a record not of origin, but of survival. Atlas's data is still being analysed, its composition modelled, its trajectory traced backward across the Milky Way's gravity map. Each simulation produces a different answer, a different hypothetical birthplace, a different history. But the truth may be that no single birthplace defines it anymore. It's a traveller's paradox. The longer you wander, the less you resemble where you began. So the next time the solar system is visited by an interstellar object, and there will be a next time, we'll look not just for clues of its home world, but for signs of its long voyage through the galactic night. Because 3I Atlas changed the question entirely. The mystery is no longer simply where did it come from? It's what did the galaxy do to it on the way here? And as that realization settles in, a quiet awe follows a recognition that the universe's travelers are not just messengers, but metamorphs, reshaped by the very cosmos they cross. By the time 3I Atlas rounded the sun, its strange behavior had already made headlines. Its brightness had surged without warning. Its chemistry looked alien, even by cosmic standards. Its tail, or lack thereof, defied everything astronomers knew about how comets behave near a star. And so, inevitably, the speculation began. Because when something from another star system acts in ways we can't easily explain, imagination fills the vacuum before equations do. It started the same way back in 2017 with the first interstellar object ever detected, 1I, Oumuamua. When it sped through our solar system, it moved like a comet but left no tail, brightened in flashes and then accelerated slightly as it left without any visible jets of gas. That tiny anomaly was enough to spark one of the most famous scientific debates of the decade. Harvard astrophysicist Avi Loeb suggested that Oumuamua's motion could, in principle, match the behavior of a light sail, a thin reflective sheet propelled by sunlight. He didn't claim certainty, but he asked a question that made many in the community uncomfortable. What if it wasn't natural? The controversy divided astronomy. Some saw his openness as bold scientific curiosity. Others saw it as premature speculation. But when 3I Atlas arrived, those old debates resurfaced with new fuel. After its outburst, Professor Loeb published a short discussion paper through the Harvard-Smithsonian Center for Astrophysics website, noting the object's peculiar resistance to the sun's heat. Atlas, he argued, seemed to have taken what looked like a direct solar storm, hit a blast of charged particles and radiation, and yet it held together. He raised the possibility that the object's structure might include materials or layering that made it unusually durable, far beyond the thermal stability of ordinary comet nuclei. Could it, he wondered, be an ancient fragment of artificial construction? Loeb was careful with his language. Not evidence of aliens, he emphasized, but a case worth considering under the same logic we apply to any unexplained data. His stance was that extraordinary claims require extraordinary evidence, but evidence still begins with asking the uncomfortable question. The idea, if interstellar travel is possible for objects of natural origin, why couldn't it also be possible for objects of technological origin, debris, probes, or relics from civilizations long extinct? Most scientists disagreed. To them, Atlas's oddities were fascinating but explainable, just not easily or immediately. Cometary activity is notoriously unpredictable, and interstellar conditions add even more complexity. The leading theory among planetary scientists points to thermal stress and volatile layering. The outer crust of Atlas, lightly enriched with carbon dioxide and carbon monoxide ice, may have acted as a temporary pressure seal. When solar heating breached that layer, gases beneath it exploded outward, creating a surge in brightness. The missing dust tail? Possibly the result of a surface so heavily irradiated that its grains fused together, less dust, more gas. Others propose that its rotational dynamics, fast spin, uneven torque, produce the apparent pulse in light emissions that some early analyses picked up. In short, physics can explain the strangeness without invoking extraterrestrial technology. But the debate itself served a purpose. It reminded scientists and the public that discovery begins at the edge of the known. Part of the allure of the artificial origin idea isn't that it's the likeliest answer, it's that it's the boldest. The universe is old enough, vast enough, and complex enough that, statistically, other civilizations should exist. And if they do, their relics might drift, just like natural comets, mute, eroded, and unrecognizable after millions of years. So when we detect an interstellar object behaving unexpectedly, it's not unscientific to keep that door slightly open. It's unscientific to keep it locked. The data from 3i Atlas isn't screaming artificial, but it is whispering unfamiliar. And in science, unfamiliar is where revolutions start. By late 2025, 3 broad camps had emerged among researchers analysing the Atlas data. Natural standard comet behaviour with extreme parameters. In this view, Atlas is a conventional comet, just one that formed in a colder, carbon-dominated environment. Its composition explains its CO2 dominance and volatile reactions near the sunday. Natural, but transformed by the journey. Here, Atlas is a hybrid of origin and experience. It began as a normal comet, but billions of years of cosmic radiation altered it, turning its surface into something alien. The outburst was the result of that ancient armor finally giving way. Non-natural or technological debris. A minority view, but one that refuses to disappear. Proponents note the object's unusual thermal resilience and light curve patterns. If these persist under deeper analysis, they could hint at engineered structure, or at least composition unknown to nature. Most researchers reside firmly in the first 2 camps. But the very fact that the third is still discussed, even as a remote possibility, shows how open this field has become. The frontier of astronomy is no longer limited to the familiar. It's easy to dismiss speculation as sensational. But the history of science is filled with questions once ridiculed, later vindicated. Continental drift, dark matter, exoplanets. Each began as an idea that sounded absurd until data proved otherwise. Controversy keeps curiosity alive. It forces researchers to design better tests, refine their models, and re-examine what they take for granted. So, while most astronomers roll their eyes at the alien probe hypothesis, they also acknowledge that asking why something seems impossible often leads to discovering why it's not. And with Atlas, every anomaly deepens the mystery rather than resolves it. If somehow Atlas were artificial, it would change everything we know about our place in the cosmos. It would mean we are not the first to send messengers into the dark. But even if it's purely natural, the wonder doesn't diminish, Because what nature accomplished here, a fragment ejected from a distant star system, surviving a billion-year interstellar voyage, then exploding in the light of our sun, is no less extraordinary. Artificial or not, it's still a story of endurance, of something ancient, lonely, and inexplicably resilient, crossing the void and briefly reminding us how little we understand. In a press briefing, a NASA researcher summarized it best. Extraordinary doesn't have to mean extraterrestrial, but it should make us listen more carefully to what the universe is saying. And that's the real takeaway. The goal isn't to believe in aliens or dismiss them, it's to let evidence guide us wherever it leads, even if that path wanders through uncomfortable territory. Because science at its best isn't about certainty. It's about curiosity, strong enough to survive doubt. And 3I Atlas embodies that perfectly. A riddle wrapped in data, a cosmic question mark that refuses to fit inside any of our existing boxes. When the universe puts on a show, the climax isn't always the end. Sometimes it's the beginning of what matters most. That's exactly where we stand right now with 3I Atlas. For months, astronomers have been tracking this interstellar wanderer on its long plunge toward the Sunday. The data, the images, the chemistry, they've all been leading up to one pivotal moment, perihelion, the instant when Atlas swings closest to our star. That moment came and went around October 29-30, 2025. And now, in the days and weeks that follow, the world's telescopes are on edge. Because what happens after perihelion could rewrite the story of this object entirely. Perihelion is where the universe pushes a comet to its limits. Temperatures soar, solar radiation slams into the surface, jets of gas erupt from frozen ices that have lain dormant for billions of years. For a typical comet, it's the dramatic but predictable act of transformation, the point where the nucleus vents gas, builds a tail, and glows brightest before fading again. But for 3I Atlas, this is not a normal performance. As it swept to within less than half an astronomical unit from the Sun, the object was already misbehaving. The brightness surge, the strange chemistry, the absent dust tail, all of that was just the prelude. Now, the real question is whether it will survive this solar encounter. Comets are fragile things. They crack, fracture, even disintegrate entirely under the heat and gravitational strain of perihelion. When that happens, we sometimes glimpse their true nature for the first time, as interior layers, once hidden, are flung into space. And so, as 3I Atlas emerged from its closest pass, astronomers weren't just watching for beauty, they were watching for autopsy. The next few weeks after perihelion are what scientists call the critical post-perihelion window, a period where changes happen fast, unpredictably, and sometimes catastrophically. If the nucleus of Atlas fractured under solar stress, the debris cloud should start to spread now, revealing multiple fragments or secondary outbursts. Observatories equipped with coronagraphs, like SOHO and Stereo A, continue to track any brightening patterns. Ground-based telescopes from Chile's Very Large Telescope to Hawaii's Pan-STARRS Array have shifted their schedules to squeeze every available minute of observation. They're searching for the telltale signs, sudden fluctuations in brightness, suggesting pieces breaking apart, shifts in the tail's shape as sunlight and solar wind interact differently with gas and dust, spectral changes hinting that new material from deep inside the nucleus has been exposed, and, perhaps most intriguingly, a persistent glow, which could mean that something within the object continues to vent or react, a kind of slow-motion heartbeat in the dark. Because if the object survives largely intact, it will defy yet another expectation, one more sign that 3I Atlas refuses to behave like any known comet. This moment is not just about watching something fall apart, it's about catching chemistry in motion. During perihelion, the sun acts as both furnace and microscope. It heats, ionizes, and strips away the outer layers, letting instruments like JWST's near-infrared spectrograph and ESA's solar orbiter detect molecules that were invisible before. Astronomers hope to capture emissions from exotic compounds, cyanides, carbon chains, even complex organics that can only be released at extreme temperatures. Each molecule tells part of the story: how the object formed, what it endured, and whether anything pristine still lies beneath its irradiated crust. As one researcher put it, the sun is doing the drilling for us. If Atlas's surface shell breaks open, revealing fresher material, it could finally answer the biggest question of all. Is the object's core still chemically connected to its birth system, or has its entire identity been rewritten by interstellar travel? That answer might come not from the explosion, but from the calm afterward. Right now, nearly every major observatory on Earth and above it is watching. NASA's James Webb Space Telescope continues to collect infrared spectra whenever geometry allows, hoping to capture the cooling curve of the Comet. ESA's solar orbiter and NASA's Parker Solar Probe, both closer to the Sun than any spacecraft in history, are scanning for dust and plasma signatures in the same region of space where Atlas passed. The Vera C, Rubin Observatory, still in its commissioning phase, is on standby for wide-field imaging once the object re-emerges from solar glare. It's an unprecedented, coordinated effort, the kind usually reserved for planetary impacts or supernovae, but interstellar visitors are rarer than both. This is only the third confirmed interstellar object in human history, and it's the first we've ever watched this closely through its closest solar encounter in near real time. Every photon of data counts. The best case scenario: 3i Atlas holds together, its coma stabilizes, brightness drops gradually, and over the next few months it becomes visible again in darker skies. That would let astronomers track it for weeks longer, building a complete timeline of its solar encounter. The worst case: it shatters completely, a faint, fading debris field scattering along its orbit, too dim for even the largest telescopes to follow. If that happens, much of its interior composition data will be lost, and its precise structure will remain forever a mystery. But even total destruction would still teach us something profound: how interstellar material reacts under stellar conditions, how far alien chemistry can stretch before it breaks. For some, that's just as valuable as survival. Many people assume the story of a comet ends at perihelion. It swings around the sun, brightens, and fades into the void. But with Atlas, the real revelations could come after that moment, when the object cools, when the new gases settle, when its surface tells us how much of it remains unchanged. As it exits the sun's glare and becomes visible again to instruments like the Hubble Space Telescope, astronomers will compare before and after spectra line by line. Any differences in carbon chains, isotopic ratios, or dust polarization could reveal what truly happened inside that blinding moment of solar proximity. It's like studying a deep-sea diver after resurfacing. You can learn more from what changed than from what stayed the same. We're standing at the edge of something extraordinary, a live cosmic experiment unfolding in front of us, one that can't be repeated. Every hour brings new data, light curves fluctuating, thermal readings shifting, spectra stretching into wavelengths never seen before. Somewhere in that noise might be the answer, not just to what Atlas is, but to what interstellar visitors really are. Are they ancient comets, rewritten by radiation, fragments of planetary formation from forgotten stars? Or, as the boldest voices still whisper, remnants of something else entirely? Whatever the truth, the next few weeks could hold the key. Because for the first time in history, humanity is watching together, globally, in real time, as a visitor from beyond the stars faces the full fury of our Sunday. And whether it shatters or survives, 3I Atlas has already done what no other interstellar object has before. It made us feel viscerally that discovery isn't just something that happens in the past. It's happening right now. So stay tuned. This story isn't over. The next data transmission, the next image, the next unexpected spike in brightness, any one of them could change everything. There's a quiet moment after every great discovery when the data fade, the telescopes cool, and the night sky returns to silence. It's in that silence that the deeper question lingers. Why does this matter to us? 3I Atlas is millions of kilometers away. It won't collide with Earth, won't brighten our skies like a famous comet, won't even be visible to the naked eye. And yet, it may be one of the most important visitors we've ever encountered. Because it doesn't just come from another place in space, it comes from another story, a piece of another solar system, drifting between stars, carrying the chemistry and memory of worlds we will never see. When we study 3I Atlas, we're not just learning about a rock, we're learning about ourselves, where we came from, and what we're part of. Every interstellar object is a message written in matter. 3I Atlas was born around another star, a long-vanished sun, whose planets, asteroids, and comets were flung into the void when that system was still young. Somewhere, perhaps 10 billion years ago, something violent happened there, a gravitational dance, a planetary migration, a stellar explosion. And one tiny fragment, frozen, unremarkable, unnoticed, was thrown outward. It drifted through interstellar darkness for millions of years, untouched, until by pure cosmic chance, its path intersected ours. That means this object has travelled farther than any probe we've ever built. It's a relic from a place light years away, and now it's giving us a physical sample of another solar system, delivered right into our cosmic backyard. When scientists point telescopes at 3I Atlas, they're studying alien material directly, not through starlight or spectra alone, but through something real, tangible, crossing our sun's domain. In a universe where distances are almost impossible to bridge, that's nothing short of miraculous. We've always wondered how unique our solar system really is. Do other stars form planets like ours? Do their comets carry the same ingredients for life? Or are we some rare exception? Interstellar objects like 3I Atlas are the missing pieces in that puzzle. By comparing their chemical fingerprints, the ratios of carbon to oxygen, the presence of organic molecules, the way ices sublimate under heat, we begin to see how nature builds across the galaxy. Are the building blocks of life common? Are planetary systems following similar recipes? Each new detection tells us a little more about the diversity of worlds beyond our reach. The first interstellar visitor, Oumuamua, shattered our assumptions about shape and motion. The second, 2I Borisov, looked more like a traditional comet, but with an alien chemical mix. Now, 3I Atlas blurs the line between both behaving like neither, teaching us that maybe our categories were never quite right. Every time we think we've figured it out, the universe hands us another reminder: you've only just begun to understand. Studying something like 3I Atlas isn't just about astronomy. It's about perspective. It reminds us that our solar system is not isolated. We are part of a galactic ecosystem, one where material constantly moves, trades, collides, and evolves. Some of the atoms that make up your body may have once belonged to other stars, other systems. Objects like this are the proof. They show that the galaxy is not a static place, but a living, circulating network of worlds and fragments, all connected by gravity and time. In that sense, 3i Atlas is a mirror showing us that the things we study out there are not separate from us. They're the same story, just told from another chapter of the universe. What's remarkable isn't just that 3i Atlas passed by, it's that we caught it. We noticed a faint, fast-moving object against the background of stars, realized it was from beyond our solar system, mobilized a global network of observatories, and within days began decoding its composition. That's not just science, that's human coordination on a planetary scale. It's what happens when curiosity wins over indifference. Every observation, every spectral line, every image pulled from the solar glare represents thousands of hours of effort by people who will never meet astronomers, engineers, data analysts, students, all chasing a mystery that offers no reward beyond understanding itself. And that's why it matters, because in studying 3i Atlas, humanity has once again proven what makes us unique among the stars: the desire to know. We still don't know what 3i Atlas truly is. A comet? An icy asteroid? A hybrid of both? Or something entirely new, a fragment of alien geology we don't yet have language for? But the beauty of science is that uncertainty isn't a failure, it's an invitation. Each time we meet a new interstellar visitor, we refine our methods, we design faster alert systems, better tracking software, more sensitive instruments. We prepare because there will be a next time. The Milky Way is filled with debris like this, millions of fragments crossing the spaces between stars. We've just started to notice them. The next one might come in 5 years or 50. But when it does, we'll be ready because of what we've learned here, now, from 3i Atlas. In the end, this isn't just a story about space. It's about what happens when we look up and remember that we're part of something vast, ancient, and ongoing. Atlas didn't visit us to give answers. It came to remind us of the questions. Where did we come from? What else is out there? How far does curiosity reach before it fades? And maybe most of all, what happens when the next one appears and we get another chance to listen? So as 3i Atlas fades into the cold and quiet beyond Neptune's orbit, leaving behind a trail of data and wonder, the story doesn't end. It only widens. Because the next object, the next messenger between the stars could already be on its way. And when it arrives, we'll know what to do. We'll aim our telescopes, open our instruments, and look with clearer eyes. We'll remember what 3i Atlas taught us. That discovery isn't out there somewhere, it's within reach, if we're willing to notice. So keep watching the sky, keep asking questions, and keep that sense of wonder close, because in the grand silence between the stars, curiosity is humanity's loudest signal.